So welcome to our next lesson on resonant structures. And we kind of introed this in the lesson on formal charge. But today our goal is to be able to draw kind of the possible resonant structures for a given molecule and then draw kind of a resonance hybrid. And the last learning target we'll save kind of for the next lesson, since we'll break this lesson into two different parts. And so just a reminder kind of from our one of our previous lessons is that resonant structures represent how the pi electrons from those double bonds can be spread or delocalized or arranged over different regions of a molecule. And the resonance hybrid kind of gives us a better picture of the molecule as a whole. So our little illustration kind of over here on the right, what that's showing us is that for the ion carbonate, that -1 charge is kind of spread across the 3 oxygens on the outer parts of the atom. As a result, it each looks like they participate in a double bond, seeing as that double bond could occupy any of those positions. It can be going to the top oxygen, to the one on the left, to the one on the right. And so overall, what that means is that the molecule tends to have 3 bonds that are stronger than a single bond, but weaker than a double bond. And as a result, instead of each oxygen having 1 negative charge to itself, they end up being about kind of a 2/3 negative charge, because at least in one of the resonance structures, they are all neutral at some point. Okay? And so the next part of this kind of lesson is from chemistrysteps.com, a great, resource if you ever find yourself taking a more in-depth kind of organic chemistry course. But we'll use some of their text and examples kind of as we go throughout. All right, so how to actually draw, these structures correctly. So as long as we keep the atoms connected the way they are, we're free to kind of change how the electrons are distributed in the molecule and show it in more than one form. These two structures are called resonant structures or resonance forms of the same compound. And we separate them using a double-headed arrow. So again, if you look in the examples, notice that the only thing that's different is the way the electrons are arranged. All of the atoms are connected in the same order, all right? And that's the idea. We want the compounds to be identical in their atom arrangement, just different in how the electrons are distributed. For example, in this first molecule, everything has a neutral formal charge, while in the second molecule, kind of that formal charge has been separated into a negative charge on oxygen, a positive charge on carbon. And so when we're kind of going between resonance structures, we'll typically use what's called curved arrows. So they kind of look like this, what you might think when it says curved arrow. And they'll show how the electrons, quote, move to different regions within the molecule. And technically, the electrons don't really move this way in real life. We just need some sort of system for tracking them, on paper. And so every curved arrow will have both a head and a tail, and that will show how the electrons flow from high density at the tail to low density at the head. And if you kind of get this concept that electrons will move from where there's an abundance to where there's a need, then you can be very successful kind of in figuring out reactions and figuring out brand new molecules that you may have never seen before. All right. And so just right quick, where are some places where there are high densities of electrons? So typically, you have electrons where there's a lone pair or where there is a double bond. So a lone pair, a double bond, and actually let me give you just one more, or where you have a negative formal charge. On the other hand, where you have low density is typically kind of somewhere with a positive charge, or where you have kind of a p orbital that can accept that new charge, all right? And so we always want to start our arrow at the high density and end it at the low density. And so we've got some examples here. So we have, in this first example, we have a lone pair on carbon 1. And so what we're showing is the movement of that extra electron density to form a new bond between carbon 1 and carbon 2. Now, if we kept both of those double bonds, that would kind of create a carbon with 5 bonds, which has way more than 8 electrons for its octet. That's a no-no, so those electrons on the other side also have to move as well, and they get moved over to the nitrogen, which then gives it a negative formal charge. So we're passing that negative charge from the carbon on the left to the nitrogen on the right. Then we have another example here, where we have electron density being passed from the nitrogen's lone pair to form a double bond, and then the double bond between nitrogen and carbon, those electrons get localized kind of onto the carbon to give it a negative formal charge. So again, those arrows, what's consistent is they're starting from either a lone pair with kind of a negative charge area or a double bond. Okay. So again, kind of 3 rules that we'll follow as we do some of these practices is if the element is on the second row, like carbon, nitrogen, oxygen, you cannot give it, more than 4 bonds. You can't give it more than 8 electrons. Single bonds cannot be broken or redistributed, and we also cannot change how the atoms are connected. So let's go ahead with that in mind and do a little bit of practice. All right, and so there's a hint at the top there. It says resonant structures involve a pi bond one way or the other. It's either making a bond, breaking a bond, or both. Those pi bonds have p orbitals that allow the electrons to be delocalized. Therefore, whenever we're asked to draw a resonant structure, look for a pi bond. All right, so that's kind of the common factor here. So our questions say, for each pair, determine if they are resonant structures of each other or not, and if they are, draw the curved arrows to confirm the movement of electrons. So in order for them to be resonant structures, the atoms must stay connected in the same way. So the atoms stay connected in the same way. The only thing that's different is how the electrons are distributed. Okay. All right, so let's start with part A. So first of all, it looks like the atoms are connected in the same way, so that's good. So now let's try to draw some arrows and see if we can start on the left and end up with the structure on the right. So on part A, we have kind of 2 structures there. Or 2 electron-dense regions. We have the lone pairs on the oxygen and then also the double bond. So it looks like in the final structure that extra electrons have been transferred to that oxygen on the top. So they must have been moving the electrons from the double bond to the oxygen. Those 2 double bond electrons now becomes another lone pair and gives that oxygen a -1 charge. Now technically what should happen is that carbon at the bottom should develop a positive charge because technically it should just be left with 3 bonds there. However, kind of somehow, this funny double bond has somehow made its way into the molecule, even when that wasn't possible. So these are not, in fact, resonant structures due to this extra addition of a double bond kind of out of nowhere. All right, let's go on to the next one and try example B. All right, so far so good. It looks like our atoms are connected in the same way. So let's go ahead and see if we can move some electrons and get us to where we need to be. All right, so we have electrons here in our double bond regions. And what it looks like, kind of based on our second structure, is that the double bonds are kind of being shifted kind of one to the right. So let's go ahead and kind of try this. So we'll take this double bond and kind of move it over here. That's where we get the positive for this carbon on the left. But then, if we try to move the second double bond, here's what we have to think about. This carbon at the end already has 3 hydrogens. And if we transition that other double bond there, that gives it 5 bonds, which exceeds its octet. So again, this transition is not possible. All right, so let's see if we can go on to C and maybe be a little more successful here. All right, So far so good. Looks like we have the same connectivity of atoms. So now let's try to go ahead and move our arrows. So let's see if we can get a hint as to what's going on in this last portion here. So it looks like what they're needing us to kind of remember is that this CN, that really is a triple bond that's happening there with the nitrogen having a lone pair. So it looks like nitrogen has gained an extra lone pair here. So we must be using one of those triple bonds to donate that lone pair. All right, so that looks good so far. Then what must be happening kind of on the second part, if I kind of redraw the molecule here, here's our oxygen, is, redraw that, there we go, is this double bond must be coming to form the bond between these two carbons now. Then what we see happening is this electron from oxygen then kind of comes to take the place of where that double bond had left off and forms a new double bond, and that leaves oxygen with a positive charge. And so it looks like everything kind of matched up with this structure. So yes, they are resonant structures, and those three arrows kind of show the electron motion from the oxygen on the left all the way to the nitrogen on the right. All right, let's pop over and do the next ones right quick. So we've got, so let me zoom back in, sorry. We've got OH here, and we've got a ring. All right, so let's see what we can do with this. So on the left, oxygen is starting with a positive charge, so that's not really a good starting point for electrons, but we do have some double bonds that are involved with the molecule. So if we notice on the second structure, this carbon is left with a positive formal charge, which means it must have lost or transferred electrons away from itself. So it looks like what's happening is it's going to start kind of by transferring its electrons to this position. Then it looks like this double bond kind of transitions its electrons up to become another lone pair on oxygen. And so that looks good to go. So these are resonant structures, and we used our arrows to show the flow of electrons. All right, now on to part G. So on this one kind of has a problem from the get-go in that the connectivity of the atoms has changed. This first structure has a hydrogen attached to the oxygen while the second structure does not. Because the atoms, the way they're connected, are not the same, this cannot be a resonant structure. Then last, let's give H a try here. So we have some double bonds, and then we also have a positive charge. Okay, so it looks like we could maybe move this double bond over to kind of satisfy that need for electrons on that carbon. So that would create this double bond here, okay? And then we likewise could move this double bond kind of over to form the new double bond that we see there. However, this kind of negative charge shouldn't be there because if electrons are being transferred away from this carbon, this should develop a positive charge instead. All right. So now what we're going to do is we're going to stop kind of on this part of the notes, and we're going to kind of pause the video, and your practice assignment will be to try kind of the resonance whiteboard problems from the PowerPoint. So when you go to your Google Classroom page, it will have a link to resonance whiteboard practice problems, and it'll take you to a PowerPoint, or in your case, a Google Slides presentation. And it has a few different kind of molecules, I think A through H, and the instruction slide is in green. And so what you'll do is you'll kind of take out just any sheet of paper, and for each molecule, you'll draw in any missing lone pairs. Then we'll use arrows to show how the electrons can transition to make a new resonant structure. Then we'll draw the new resonant structure, and finally, check your answer kind of with the next slide. And so then you can upload a picture of your paper to Google Classroom to kind of show where you've practiced. And so it's a good idea when you're doing this to kind of do it in present mode. That way you can't see the answers in advance. So what we'll do first is we'll add in any missing lone pairs. So oxygen, it has 4 electrons from its bonds. And so it needs kind of 2 additional lone pairs there. So we'll draw those in. Now what we need to do is use our curved arrows to show how the electrons move. So we know the electrons will come from a region of high density, like a double bond or lone pair, and transfer to a region of low density, like a positive charge. So here we'll have the electrons kind of transition, and what they can do is form a bond that will help satisfy or stabilize that positive charge. So we'll draw the molecule kind of in that new arrangement there, where we have a double bond. We'll have 1 lone pair left behind. Then we'll have to reaccount for our formal charges. So here for this top oxygen, it starts out with 6 valence electrons, and it has 1, 2, 3, 4, 5. 6 minus 5 gives it a positive 1 formal charge. And then for this carbon, if it had a positive charge before, it probably just had 3 bonds. All right. So we can assume there was a hydrogen there. And so now, if that hydrogen is still there, it would have 4 bonds, meaning that it's now neutral. So the oxygen has transferred electrons to make a new double bond to the carbon, and it's now taken on that positive formal charge as a result. Then we can go ahead and check our answer on the next slide. And again, at the beginning, as you're going through these, they're probably going to be, a little fuzzy. You may not always get the right answer on the first try, but just kind of the more you see, like the answers and the patterns, it'll kind of start to click, hopefully a little bit better. All right, so good luck when practicing. And again, definitely email me or come to office hours if I can help you with any of this material.